I assume the time at Germany is like in the afternoon, right? So good afternoon, everyone. My name is Songhao Bao, currently a PhD candidate at Department of Chemistry, University of Waterloo. The topic of my presentation today is time-dependent vibrational electronic coupled cluster, or VECC theory for non-adiabatic nuclear dynamics. My disciplinary and the topic is rather different from most of the other audiences and speakers. I study computational and theoretical chemistry, and we develop computational methods that could facilitate experimenters to simulate their phenomenon and design novel materials. So to begin with, this is the outline of my presentation. And firstly, I'm going to talk about the motivation. I'm going to introduce what is non-adiabatic dynamics and why we're interested in this phenomenon. And also I'm going to talk about how in practice people could construct those vibronic models to simulate the dynamics of it. And I'm also going to discuss about some conventional methods used to simulate this non-adiabatic dynamics and what are their limitations. So as you know, in general, in physics and chemistry, there are a lot of phenomena associated with light. Basically, the molecule could absorb light to exactly from the ground state to excited states. And those phenomena normally associated with multiple excited states, electronic states, that is also associated with vibrational levels. And applications of non-adiabatic dynamics, including simulating vibrational resolved electronic spectra, as well as some other time-dependent properties, such as state population. By quantitatively understanding those properties, experimenters could gain insights on some photoelectron process, and it could help them to design novel material, such as photocatalysis or some photoelectron devices. And normally, when simulating this vibronic spectra, a conventional Frank-Condon model is introduced. This model is under Born-Oppenheimer approximation, where the electronic wave function is assumed to be decoupled from nuclear wave function. And people could make this assumption. That is because normally the energy spacing between electron states are much larger than that of vibrational levels. And the vibrational levels serve as fine structure in their absorption spectra. And under Born-Oppenheimer approximation, the potential energy is a function of a nuclear coordinate. This is known as PES, or potential energy surface. And also, in this Frank-Condon model, electrons are assumed to be vertically excited from the ground state surface to the excited state surface. And this diagram shows how a Frank-Condon model works. Basically, this is a ground state surface, and this is an excited state surface. And the molecule absorbs light, and the electron could exit from the ground state surface to excited surface. And the intensity of the absorption is dictated by Frank-Condon factor, which is a product of transition dipole moment and the overlap between initial wave function and the final wave function. And the Frank-Condon model works for VECC coupling systems. However, in the case where there are multiple close-laying excited states, this model becomes invalid because the Born-Oppenheimer approximation became invalid. But that's the goal why we need to introduce more complicated models. And those models are known as vibronic models. And in these models, we assume that the nuclear wave function is coupled with electronic wave function. And typically, those kind of systems have multiple close-laying excited potential energy surfaces. And those surfaces has crossing points. Those crossing points are known as quantum intersections. In practice, there are some difficulties to directly compute or construct those model Hamiltonians using adiabatic basis. This is due to this non-adiabatic coupling constant, or NAC, is proportional to the gradient of the potential energy surface. at the quantical intersection, the potential energy surface normally has sharp turning points, which may cause divergences at those points. And in practice, people conduct a procedure known as diabatization, which is a unitary rotation of electron surface to eliminate the NACs and to form a matrix potential. And this potential is always a smooth function over nuclear coordinate. In this way, people could get rid of the divergency issue when constructing the vibronic models in adiabatic basis. And this diagram shows the potential energy surface represented in adiabatic surface and diabatic surfaces. And in adiabatic surface, as you can see, S1 and S2 are two excited states. Both of them are complicated curve, and both of them have sharp turning point at the conical intersection. However, if we represent the same potential in diabatic representation, both of the two excited state surfaces are smooth parabola. And assuming there are many efforts has been made to efficiently construct those vibronic models, and this is not our goal. Our goal is that assuming we have those model Hamiltonians represented in diabatic basis and simulate the dynamics of it, or solving the time-dependent Schrodinger equation. Conventionally, there are a class of approach known as multi-configurational time-dependent Hartree or MCTDH approach has been a successful approach to simulate the non-adiabatic dynamics and has been developed for decades. The good feature of MCTDH is that it's variational. In principle, under infinite basis set limit, it could always converge towards the exact solution to Schrodinger equation, which means it's very exact. It's very accurate. However, there are some limitations of this approach. Firstly, though it has many efforts to reduce the computational cost, but in the worst case scenario, MCTDH has exponential scaling over the size of the system. What's more, to investigate relatively larger systems, people normally need to have complicated multi-layer settings, and those settings are based on physical intuition, which are not user-friendly. And those are the major motivations for us to develop another alternative approach that could avoid exponential scaling and become more user-friendly. And now let's talk about our approach. We call it Vibrational Electronic Coupled Cluster method. And the essential idea of this approach is instead of using this full CI ansatz, we apply second quantization operators to parameterize the time-dependent wave function. And in this way, we could avoid exponential scaling. As you can see here, there's an analysis of the full CI ansatz or basis set-based ansatz and our coupled cluster-based ansatz. And in the full CI ansatz, the number of the complexity or the degree of freedom to parameterize the time-dependent function has exponential scaling over the size of the system. However, in our CC method or VECC method, we only the complexity or degree of freedom to parameterize the time-dependent wave function only scale classically or polynomial. In this way, our approach has the potential to simulate much larger system with much more efficiency. And you know, the idea is simple. However, to make it into practice, there are a lot of technical details we need to resolve. And to discuss those, we'll just cover some of those difficulties. And to start this long journey, you know, this project has been developed for 2 or 3 years. To start this long journey to developing this method, we firstly started from a simple reduced problem, which is a single surface vibrational problem. And in this problem, we assume there's only one excited state electronic potential energy surface, and the wave packet would moving back and forth within this surface. And the Hamiltonian of it could be represented by a general displaced harmonic oscillator, and it could have multiple dimensions. And a quantity we are interested in is known as time autocorrelation function. And by the spectra could be generated through Fourier transform of this quantity. And we use this problem as a prototype to test the different ideas or different answers, and finalize our choice of answers, and then extend it to the full vibronic coupling problem. And due to the time limit, I won't go into details on those answers, but we propose 4 answers. Each of the new answers is trying to improve one aspect of the previous one. And the general design principle is to make a balance between numerical robustness and accuracy. Basically, this first answer, which is a single exponential answer, is very accurate. However, it is lack of robustness. However, the linear CI answer is opposite. It has good robustness but lose accuracy. Then we design another answer which combine these 2 parts together to trying to combine the good feature of these 2 answers. And finally, we have one more refinement, which is we call it modification of projection manifold. It is this final refinement that make our approach work and extend it to the full vibronic coupling problem. And I will skip this part and let's show some results. So we tested on a simple 2-dimensional vibrational problem. And as you can see, a good feature of single exponential answers is that it's just a numerical exact. However, there are some numerical divergence issue when directly extended the single exponential answers to full vibronic coupling problem. On the other hand, in the full CI, in a linear CI answers, it has robustness. However, comparing to the exact results, it has large deviations. And so we need further improvement. And as you can see, this mixed CCCI answers, we call it in this way because they combine these 2 parts together, has a great improvement in terms of accuracy comparing to the linear CI answers. And however, it's still not good enough. And there's still some robustness issue when being directly extended to the full vibronic coupling problem. And then we introduce the final refinement, which is this modification of projection manifold. And it is this final refinement that makes our approach work. As you can see the plots here, the orange curve is the linear mixed CCCI answers adding this final modification, and the green curve is the mixed CCCI answers without this modification, and there's a great improvement in terms of accuracy. And after exploring different answers using this prototype problem, we extended to the full vibronic coupling problem. In this problem, instead of there are single excited states, there are multiple excited states, and the wave packet could moving back and forth within these different potential energy surfaces. Since in their Hamiltonian, they have surface couplings, and the wave packet could hopping between different surfaces. And this is a general Hamiltonian that representing second quantization to describe this type of vibronic models. And comparing to the previous case, the additional thing is the sum over AB, and those sum is over electronic states. And we also interested in this quantity that is known as time autocorrelation function, because we want to simulate spectra, and spectra could be generated from Fourier transform of it. And so due to the time limit, I also don't want to go to details, and there are very complicated mathematics. You know, as a theoretical chemist, mathematics is our common language. And so the major complication is that in the full vibronic coupling case, we just need to introduce multiple electronic surfaces, and we need to sum over all the surfaces. And the only additional refinement comparing to the previous simple reduced problem is that we introduce this even faster parameterization on coupled cluster amplitude. And the even fast dynamics has been applied in conventional ab initio molecular dynamics, which evaluate four forces at each time step by taking the state average over all the surfaces. And here we do something quite similar. We take weighted average over electronic states to incorporate the average motion of wave package and accommodate the switch between electronic surfaces. And basically, we could solving this first order time dependent Schrodinger equation is like an equation of motion, and to numerically to determine T amplitude and Z amplitude. Those are some tensors, and the time dependent properties could be mapped from T and Z tensors. And in this part, we emphasize on simulating spectra, but we could also simulate using the same scheme to simulate other time-dependent properties. Basically, this is like a definition of average value in quantum mechanics, and we could apply our coupled cluster ansatz into this expression to direct calculate all the properties, and O could be a general operator. It could service any properties of interest. And the mathematics to derive this expression is rather complicated, but we could derive a concept form of equations using this scheme. And here we use a special case as an example. We specifically interested in a property known as diabatic state population. And if we directly substitute this OR operator into this general expression, we could derive a concept form of state population, and we could implement it into our program. As we know, the diabatic state population is an important property that is of interest. It tells how the character changes along the time about of the wave packet within the excited state surfaces, and this information could help people to understand how the excited the wave packet hopping between surfaces. And it could be applied in many applications to understanding many photoelectron processes, such as designing photocatalysts. And now let's show some major results. We implement this method and benchmark on a few molecular compounds. This is are the three compounds we benchmark with. The water molecule and ammonia molecule, and we also benchmark with this challenging model with 14 surfaces and 63 moles. And as far as we know, this is one of the largest vibronic models that have ever been investigated using conventional MCTH approach. And this is the spectra. We benchmark our VECC approach with MCTH, and this is the absorption spectra of water molecule. As you can see, our approach just matches MCTH, and we also compare it directly to experimental spectra, and they both roughly matches. And we also investigate the diabatic state population of water molecule. As you can see, if we initialize from first two states, we won't see significant character changes. However, if we initialize from the third state, there are rapid, comparatively rapid character change between the third state and the second state. And this tells some information on how surface hopping, the wave packet hopping between surfaces. And another molecule we investigate is ammonia. And as you can see in their spectra, there are mainly two bands. And as a low energy band, our approach is matches the MCTH approach in a high level. However, as a high energy band, there are discrepancies, small discrepancies on both peak intensity and the shape of the peak, and both the two methods roughly matches the experimental spectra. And as you can see in ammonia, the character changes much more rapidly comparing to water. And so this is this means that ammonia is a much more stronger coupling model comparing to water molecule. And if we initialize from the second state, there's no character changes, which means there's no coupling between the second surface and the other surfaces. And this character tells many informations. And unfortunately, we also comparing our calculations of diabetic state population with MCTH. It turns out that at short time range, our approach roughly matches MCTH, but at longer time, the deviation become larger. And this is the third model we are investigating. So this molecule is hexahelicene, and we benchmark with multi-layer MCTH approach. And we collaborate with Fabrizio Sottara's group from Italy and gain their data from their recent publications. And as you can see, our approach generally matches Sottara's results. And what's more, our approach is much more efficient. To running the same calculation, it took approximately months to get the results. However, using our approach with 10 CPU in parallel, it only took around 3 hours to run 50 femtosecond propagation. And also, our approach is much more user-friendly because the only input of our program is the model parameters. However, in Sottara's to get Sottara's result, they need complicated multi-layer settings, and both spectra roughly matches the experimental spectra. And also, this is a typical strong coupling model because if we comparing the spectra generated from Condon model, there are qualitative difference at low energy region. And that's all about the results. Now let me briefly summarize this talk. We developed an approach known as MCTH, known as VECC, that could simulate non-adiabatic dynamics. We could both simulate spectra and other properties. And the good feature of it is classical scaling, and it is much more efficient than conventional approaches. And here are some future works. As I mentioned before, the scheme that we propose to calculate properties are quite general, but here we only give a specific example to calculate diabetic state populations. But in principle, we could also calculate other properties of interest. And also, one of the limitations of our current approach is that we could only dealing with second order harmonic oscillators, harmonic potentials. And my colleague and I are collaborating to develop a equation code generator that could generate equations, the working coupled cluster equations for any order of Hamiltonian with any order of truncations. And in the future, we could extend our approach to more generic form of Hamiltonian and higher order truncation of coupled cluster amplitude. In the end, I want to give thanks to my supervisor, Professor Marcel Nowogin, who is giving us high-level instructions on theory and always full of brilliant ideas. And also give thanks to my colleague Neil Raymond, who is one of the major developer of these projects. And he also leads the project to develop the code and equation generators, which makes us to implement this method much easier. And our code is available on a Git repository. If anyone are interested in our work, we are glad to share our code and do some collaborations. And this research is sponsored by NSERC. Here are some references of this presentation. Thanks for listening. Any questions?
Thank you so much, Doc. So floor is open for the questions if anyone having the questions. I can't able to see any questions. If anyone having questions after the chat also talk, then you can type over the chat box. Doctor will respond there.
Yeah, we have a question. Yeah. Yes, you.
We having the questions for you.
Yes, we have a question.
Okay, please go ahead.
This is whether you can bring the NH bond to such vibrations that it breaks. It would be really interesting for like hydrogen carriers. Thank you.
I think at present we could only do quadratic or harmonic potential, but I think for bond breaking, this approach might be have some limitations. But I think the structure needs to be a hard structure, not a soft structure. Like if there are some mechanism associated with rearrangements, maybe there's some difficulty to incorporate those effects. And also there are some, I think the bottleneck is to construct those vibronic models. You know, the diabatic procedure might not converge, and yeah, it's complicated. The simple answer is it might be challenging.
Thank you.
You're welcome.
Any further questions from the floor? I can't see any further questions. Thank you, Doc, for your